Oh, that's nice. You got windows open. That's better, but a little bit of yeah, otherwise it's
I want to bring up another topic which we have found to be actually extremely useful. We dabbled in this while we worked in this for many years. But it's just that everything, there's this line that comes when something really actually can make an impact. And I feel that just this ability to change polymorphs, get a different kind of structure, and implement some sophisticated problems is holding quite a lot of confidence. So I'm going to show you what we've been doing and talk about all we can learn. So here's the outline. I want to first of all talk a little bit about why L2, we've been using it. Why should we do something else? Talk a bit about LP norms. We'll revisit the 2D crosswell topography. And I'm going to go back to the magnetics. And then we've got a 3D gravity data set at Kibitsa that we'll show. So LP norms, what we've been doing up until this point is to just kind of continue with everything being squared. So we've got this kind of objective function, we discretize it, and we can write this model objective function as the sum of these different components, the smallest, smoothness in X, Y, and Z, and write it like that. And we talked this morning about changing the alphas and changing the W's. Like, okay, is that enough or not? And that's still a question. But I think I'm going to show you that we can actually do more by simply changing the sum. So let's just go back and take a look at what we've done so far. So here is our 1D inversion. So kind of got a good general representation. Good data misfit. Here's our Tikhonov curve. So that was fine. We didn't really get these sides very well. Did the 2D crosswell, and we got something that's concentrated in here, but not exactly like that. And then we did the 3D magnetics. And we got, with the sensitivity, that's something that kind of looked like that. Not bad, but still wasn't, wasn't great. So then the question is, well, what is missing in like 1D, 2D, and the 3D? And the thing that you see is that in the L2 norm, it really hasn't, because we're working with the smoothness term, it really smooths out any kind of sharp boundary. So if we got something that looks like this, it will always smooth it out. Okay? It can have artifacts. We saw that there was negative values that were coming, and we've got, in fact, you can kind of consider this negative value here as a little bit of an artifact. And it can violate the physics sometimes, negative susceptibility. So it's good. The L2 is good, but it's not perfect. What can we do there? So let's just kind of look at our general norm. So far we've used L2, so we take this, we discretize it, and we end up with something that looks like this. So now it's just the value squared. these VIs are volume terms, right? Because we're always trying to represent the value of some integral. And when we discretize it, then we need the volumes of the cells. The general LP norm, instead of having it squared, has just got an absolute value here and raised to some power p. So that's a different measure. And if we took even this model that we've got here, and we evaluated it with, we evaluated this with p is equal to 2, we get a number of 69. P is equal to 1, we get 55, 0.5, 54. P is equal to 0, we get 100. So each of these, remember we were talking about rulers this morning, like how do we measure the length of something? Each of those is a different ruler. And so in one case, with this particular ruler, you might be the smallest. If I change the ruler, then somebody else is different, right? So that's the idea here. And now the question is, how do we really employ that? The thing about the LP norm is that it changes the character of the model. So let's suppose that we're just thinking about the smallest model component here. So here is 5. With the L2 norm, we're basically trying to make everything equal to that reference model or 0. And that just sort of flattens out. If we chose to do p is equal to 1, we minimize that, then p is equal to 1 gives you a sparse solution. It's a sparse solution in which you're guaranteed that if you do linear programming, it guarantees you that the number of non-zero elements is less than or equal to the number of data. So p equals 2 minimization gives this. P equal 1 would give something that looks like this. And a p is equal to 0 gives you a solution with the minimum support. So in other words, the fewest number of non-zero elements that could give a solution and come out in it. So that's the difference in character in that smallest model component. If you transfer them to the flatness term or the smoothness term, what you notice for p is equal to 1, you have only a few places that are non-zero for the smallest model. So now if you kind of think about, that those are applied to the derivative, that means that there's only going to be a few places in which there's going to be a change. So the model will be much more blocky. And for p is equal to 0, means the fewest numbers of changes of derivative are going to be so it changes the character. So those are the things that are kind of important, and you can see why they might really be useful. I must admit, this one here has been very useful at sparse like representation of seismographs, because there you've got reflectors that are coming in. And so your model is really just sort of impulses. So sometimes the right kind of norm is just perfect for a particular problem. So with our general objective function, we've got something now that looks like this. So phi m is just a sum of all these guys, where fj could be the model. Or it could be m minus f. Fx could be the derivative with respect to x, fy, derivative of y, and then derivative. So we've got like 4 of these guys, and each with a different quantity in here, and each potentially with a different p-value. So we can write this as phi m is the smallest model component, but now evaluated not with L2, but with Px, some p-value between 0 and 2. X derivative, evaluated now not with P, but Px. y, and z. So great flexibility, right? Because each term can now have its own representation of power for the LP value. So why does this happen, and what are the implications? If we look at the peak power of variables, not just think about a single value of m here. If p is equal to 2, we have this quadratic. And when values of m get larger than 1, then there's a real high penalty on it. So L just like very large values. As p goes to 1 or half, then penalty, the value of the penalty is going to in a different manner. So this is effectively what the ruler is like when you're evaluating the model with respect to peak power. We're going to need to calculate the derivatives because we know we have this thing, but then we want to compute change of the objective function with respect to the change of m. So we need to do a derivative. Now, if I take the derivative of this, analytically, I could say that it's p and p minus 1 times. This is the sine function. And it actually has a lot of difficulties right around m is equal to 0. So rather than trying to work completely with that, it's easier to do something that's approximate. So we're going to introduce another norm. Actually, it's first introduced by a guy by the name of Watts. And it said that the p norm here is actually going to be represented as m squared, okay, divided by this quantity here. So if p is actually equal to 2, then you got 1 minus 1, so you just have that's equal to m squared. If p is equal to 1, okay, then this is 1 minus a half, so it's a half. And especially if you neglected the epsilon here, this little stabilizer term, then m squared to the half is m, and then m squared divided by m is 1. So this thing comes back to m equals 1. So this is a way of actually representing the p norm with epsilon being a small perturbation. And so epsilon has to be a small number. Actually, finding what that number should be is kind of a non-trivial thing, but there's ways of doing it. So anyway, we're going to replace the true p norm by something that looks like this. And then how do we solve that? Well, we're actually going to pull a fudge. Right? It's kind of like I will say, I have a hammer. Do you look like a nail, right? So we know how to solve two problems. So now we're going to recast this thing, minimize this here in this form here, where we've still got an m squared on top and then divided into itself here, so that we can write it as some matrix times m, where r is a diagonal of this guy. So it's just a little bit of smoke and mirrors as far as represented. So this one here is equal to this r like that. So r is a weighting matrix now to find the current model. And what we want to do is to solve this with iterative reweighted least squares. And so rather than evaluating m here at the current, well, making it part of the unknowns, we're actually going to evaluate this from the model we currently have. So then our problem now becomes something that looks like this. So the linear problem would be g of mk plus 1. So that's the updated model plus beta of rk plus 1 times this, where rk plus 1 is just going to be the evaluation of this at the model that we're at. So that means that we've got this for 5. We take the gradient, we get something then that looks like this. And we're going to successively solve this problem for mk plus the updated one until the difference between 2 successive iterations is less than some tolerance. So for our just to recap, we've got a general norm that looks like this. These as functions, we're going to use the loss norm like that, and then we're going to iterate using higher or less. So here's let's go back to the cross-floor topography problem. So we've got how does that function? If we do everything in L2, we get a solution that looks like this. So it's smooth. Now we're keeping everything on the same color scale here for honesty. So we've got something that's kind of in that right area, but it's low amplitude. If we change for PS, if that is actually equal to 0, but PX and PZ are 2, then we get something that looks like that. So that's actually a big difference. Notice the change in the amplitude here between this and this. And then if we go for PX and PZ equal to 1, so that's now looking for kind of like an L1 solution, so kind of sparse on the derivative. We actually end up with something that looks like that. So that is actually really nice. We've got a random character coming out as a block, and I've got an amplitude that's much higher than what we had here. That's a pretty good representation of what this is. So the color scale here, blue is 2000, and this color scale is 1800 or 1750. So that's actually a solution. Now let's go to our magnetics. So now we've got the same susceptibility block, which looks like this. And just to review where we were, we have the synthetic model. So there was the data with noise. We haven't forgotten about this depth range. Remember that sensitivity of the kernel slope Q. We captured it. So we got to keep that in. So that means that in our model respective function, still have those guys, one over RQ, and we had this big square sheet. So what we got is the sensitivity function. The inversion with sensitivity gave us something like that. All right. Susceptibility is positive. Okay, so we need to address this. And I'm not going to talk about the details of this, but again, you can implement positivity or bounds by using what's called a projected gradient Gauss-Newton. Kelly in his book 1999 talked about it, and Eldad Haber, book in 2015, talked about it. So basically, what you do is, in working with bounds, is you use kind of a combination of steepest descent and testing types of solutions, so that your delta M is made partly of gradient solutions where those cells are at the bounds, and partly of curvature Hessian solutions where you've got values that are away from those. Okay, so without going into details, we can alter what we already have without very much change in coding to incorporate positivity or bounds. So when we go ahead and do that, then without the bounds, we get something like this. And with the bounds, you can't really see it that well on this projector, but there's a much bigger, concentration of stuff that's here. And also, we don't have these large tails that come down here. So, yeah, it may not appear that dramatic when you look at it on that screen from your distance, but there is a substantial difference between this solution and. So the bounds help, but now we're also going to do something else. We're going to change our p-norms here. So now the inverse problem stays the same. It's just that we're going to change. So we have to change any of these 0, 0. And if we chose this one, let's say p on the smallness, p is equal to 0. Remember, p equals 0 is minimum score. So it gives you a solution that has like the fewest number of non-zero variables. And you can see what that is done here is really sort of sucks everything up and something that is very highly concentrated. Even though p, x, y, z are all true. So we're still asking it to be smooth, L2-ish, but really concentrated in that small. And that itself is negative. And if we do Ps equal to 0, and xy is equal to 1, so now we're kind of looking for sharp boundaries. Now this is okay. So this is actually like the right solution. I mean, consider that a big deal. And we have no solution. Yeah, being able to go ahead and get out something that looks like that. So here's the final modeling. But without any everything's got the surface because that's where your greatest sensitivities are. The sensitivity again, it goes down. Put in positivity, and you end up with something like this. Change the p value smaller than that. Also change on the derivative terms. You get that. That's a lot of change, and also potentially a lot of flexibility on trying to get different kinds of solutions out from your inversion. And yeah, if you look at the data, you're not going to find any difference. They're all the data really nicely. So in summary, we've got for LP norms, that makes it non-linear. Actually solving this problem numerically is challenging. This is one of the one of the pictures I showed you was Dominic Fournier at the beginning. He's just finishing up his PhD thesis on this, and actually trying to solve this problem numerically has challenged an awful lot of people, but I think we've got a very nice solution for that. It seems to be quite stable. And also this provides a way of exploring model space. We're talking about non-uniqueness. So we've got a couple of options. One is, like, okay, let's put in everything we got, and then get on to that. But then there's still also always some hyperparameters that we could change and try to figure out, okay, what would the effect be for them. But understanding what those parameters should do, and then just selecting judicious values and realize you can end up solving zillions of versions. But just being able to kind of parse out, if I get this parameter, this parameter, this parameter, I get spectrums of inversion results. That's really useful. I mean, it just kind of grounds you in on what to believe, what not to believe, and just how much you data are really telling you. So here's an example. So you did the gravity? Who's doing the gravity? You were doing it. Okay. So this is gravity inversion in a mine in Finland called Kavitsa. It's got a lot of nickel in it. There's a large, it's a test data set. Well, it's not a test data set. It's a test data ground. There's a lot of different kinds of data, DC resistivity and IP, magnetotelluric. There's a few people here doing MT, 3D, seismic refraction, airborne, time and frequency domain EM, magnetics, and gravity. And here is the magnetic survey over top. So this is nanoteslets. And going from 2,000 to minus 500. So it's 2,500 nanoteslets. Like
That's a real
serious
amount.
And then here is the gravity data, which is peak to trough is 20 milliamps.
So it's, again, still pretty.
So we'd like to improve this. At this point, we're going to look at the gravity data. So here's what the geology looks like. This thing is about 2 billion years old. Ultra, supposed to be that. Well, maybe depending on if they owned it or not. It's like, well. Yeah. So there's a lot of stuff happening. I mean, look, here's the geology. That's complicated stuff, right? You got all kinds of different geological units. There's sort of been a lot of folding there. There's faults. It's a mess. The one thing that they did have across here, across this profile here, was a seismic refraction survey. And this is the seismic section, this is the interpreted section. So these black lines here are somebody's interpretation of what is going on. And there's just a couple of units in here that are important from the point of view of the structural complex as well as normalization. So anyway, gravity data over that. So that's that. Right? So that looks pretty black. And you want to see if you can get some detailed geology out of that. Okay, so that's the top. So that's a whole bunch of boreholes there, a whole bunch of different rock units. From the point of view of density, there's some that are pretty low, there's some that are high. There's a number of rock units that have almost the same density, but there's variance. So take a look at the gravity data, and if you just did a smooth inversion, you do the L2 inversion, then what you end up with is this is like a surface projection of the density, and you see there's this the density anomaly in here, and there's low, there's high, and then you get a cross section slice through that, you get something that kind of looks like that. So it's very high density in these rock units over here, but there's really no delineation here, right? It's smooth. So that's exactly the kind of thing that you think about, like, oh, I want to have something that's sharp boundaries. I want to have something that's sparse, because this is not a really good. It's not providing you with a lot of good geologic information. So now we'll go and we'll do this 3D gravity inversion with different norms. So what we're looking at here is essentially the same time linearly, but with different values of P. So all of the P, X, P, Y are going to be the same, either 2, 1, or 0. And the PX is either 2, 1, or 0. So remember, at this level here, on 2, everything is smooth. Yeah. The model is also going to be close to a reference model, which in this case is kind of the 0 model. And you get something like that. as you change the horizontal derivatives, the emphasis, you start to get slightly different kinds of structure. It's not huge amount of difference on these, but there's some that are significant. And now, most important is on the smallest, as you start to decrease from 2 to 0, you get a very different kind of structure. So now, as we go from PS from 2 to 1 to 0, you can see how that L0 term is just kind of giving you like the fewest number of elements that have, essentially blue or red, and therefore you're really making this whole thing compact. And then as you also do that with the derivatives, you've got this. Okay, so that's it. I mean, all of these models that you have here, from the point of view of fitting data, are equally valid. But this is, like if you think about it, this is at least one way of starting to explore model space in some kind of linear fashion. And this is, this is what we have. But the thing that we do see is that there's really compact lithologies that are coming in here. And if we do a cross section of these, the previous one, overlay that with the seismic data, as you're going from this side here, things are becoming much more compact, and this unit here is now being bounded by this seismic trace here, and so it looks like it's actually doing a fair job of trying to pick out that dense unit. So that's pretty encouraging, and I think it shows a number of things. One is just that value of kind of exploring models, just to sort of find out what other solutions are there, but doing it in a sensible way, and also just understanding that general compactness that can occur as you get to p is equal to 0. So to put everything together, here's a plot of the isocontours of density that are coming from all of the 9 models. So kind of trying to put all of those, take those 9 different models and basically trying to put them all together and get isosurfaces that are connected with all of them. And you get something that looks like that. So that's superimposed upon the geology. So there was no geologic information that went in, but if you look at the lines of this, you can see how the arcs are coming in and actually is coinciding with geology. So that's hopeful. And you got regions in here with really negative density. Look at that's all kind of in that particular unit, and similarly back here. So I don't know, it's pretty encouraging. And on the cross section, when you look at here, you can see the really high density more or less being bounded by some of these units. So just from the point of view of working with the gravity, I think we're able to bring out a lot more information here than the region is equal. So that's it for that. So we talked about LP norms, we did crossroad topography, 3D magnetics, and we did 3D gravity at Kibitsa. So with that, I think we still have some time before coffee. So let me at least start this. So I think that actually might work out okay. We'll start this, we might not finish it, but we'll take off when coffee is here. We'll get partway through, and then we'll kind of wrap up with the future. Any questions while we change screens? Yeah.
So for pizza case, what would happen if you do not have the dumping term at all? I mean, what do you think it for you? because there's a dramatic improvement when you go to the sort of zero group.
Yeah.
With the damping, but if you wouldn't have damping at all, it would be the transformers.
Sorry, what do you mean by
the smoothly?
Pardon me?
You would only have smoothly your rotation. But would be a whole. So for you, the question is what you made in the machine by damping? Is the oil in the machine? Or
By having that, if you call damping that small component, what that is doing is trying to give you a solution that's really compact, the fewest number of non-zero elements. So it's very effective in trying to make things sparse. So it's so it is an important piece to have in the puzzle, and you have to make sure that it's effectively weighted to do that. Okay. Field scale. I must admit, whoever opened these windows, I kudos to, because that really makes it much nicer. Okay. Okay, let's just regroup a little bit. So the question is, okay, where are we? What have we done so far, and where are we going to go? So I think we've got the methodology is in hand, right? We understand the basics of the inverse problem and how to solve it. We can solve a nonlinear problem. Generally, they're voxel based, but virtually all of ours are voxel based, but most of them are connected with PDEs, but they could also be integral equations. So that doesn't matter. So that's not a big issue. The our DC resistivity, which was like this guy here, we solved using a finite law. The gravity of the magnetic we solved using an integral equation technique. So that's fine. We shall incorporate different kinds of information through the model objective function, and also incorporate bounds. And we could also change the the various norms on that model objective. So that, when you really come down to it, that's a lot of parameters even within that context to explore. But having an idea of what those parameters do is essential. And we've had a case of that sort of showed you that. So for practical applications, here's where we're going in the next decade is we're really going to be solving very, very big problems. So for instance, here's a case. This is Alberta. This was for Mauricio's benefit, but he's not here. It's Edmonton, Calgary, and what we're trying to do there, what the object was to really define the subsurface so that you can understand where the aquifers are and what the flow is and where people could drill and stuff like that. That sort of typifies then one of the problems that we're looking at, namely, large-scale airborne EM data. So here you've got data that are collected on many tens or hundreds of thousands of soundings, and you want to somehow do something with them. And this is actually a map of an apparent resistivity, but what we really like to do is to actually get out a 3D volume, okay, of electrical resistivity over this whole region. And this is, you know, a couple hundred kilometers from south to north, and maybe 100 kilometers this way. And you want to get down to, you know, maybe 50-meter resolution at the surface, or at least 100-meter resolution, and you know, good depth resolution. So if you start to think about, okay, what are you up against for the number of cells to work with this? It's like, okay, this is a seriously big problem. So the issues for large-scale problems, which airborne EM is only one, they really come in the forward modeling and in the inversion, and try to figure out how do you handle all that. We have the tools, we understand what we want to do, but now it comes down to really figuring out how we're going to do something. And then the other aspect is once you need to address uncertainties. So things that are important. We're going to explore it twice. Explore model space. Yeah, maybe we're going to parameterize things. Maybe we can reduce uncertainty by joint inversion. Maybe we can do something else with respect to looking at different physical properties. Maybe we can use spectral physics. But I kind of want to take through some of these, not in necessary detail, but I think that by the end of the day, you'll have a really kind of good kind of understanding about, okay, where are the problems, where is the problem, and how do I generally go about and address this. And then later on, stuff is kind of more details, maybe challenge details, but at least you got a global perspective. So let's just talk about large-scale airborne EM problem. Actually, who here has worked with airborne either frequency or timing? Anybody? Oh, Argentina, where are you? You're good at soccer, but I gotta be good at airborne. Okay. I'll talk a little bit about that on Wednesday. So anyway, we got a system. So this is what it looks like. So this is the bird. It's got a transmitter and receiver, and it operates at multiple frequencies. That's the frequency. This is a time. So this is a loop. That's your transmitter, and you're going to pull it. You know, you're going to drag this over. There's the receiver that's sitting right here, and actually there's the magnetometer. That's up there. So it's very easy to accumulate a large sounding 100,000. That's even for these days. Getting up multiple hundreds of thousands. And at multiple frequencies or times. So this is starting to like, okay, this is serious, big data. And that's sort of we're going to apply this to a diamond exploration project in Canada. Actually, I could talk a bit about this. So kimberlites, they're explosive events. So you've got carbon that is stable in diamond form, at 150 kilometers depth. And if you can get eruptions that bring that up to the surface really quickly, then the carbon will remain stable. And also when it gets to the surface, it's stable. So as long as it kind of instantaneously goes from 150 meters or kilometers to the surface, it can be stable. And then these are explosive types. So you've got material that explode out. And they're called kimberlites. And the K, it's kimberlite. There's different kinds of kimberlite. But anyway, you can imagine stuff explodes out, right? There's everything, right? And there's stuff that's falling down. So you kind of make a crater at the top that often fills in with a lake and maybe some lake sediment. And then you've got these different units. And different units here have different potential for having diamonds in. So you not only want to find out where this kimberlite is, but you also want to differentiate between like an HK and a BK or P. So that's the real problem. Here's the area up in northern Canada. So this is the Northwest Territories boundary. So this is the place up here. It's called TKC. It's Kleep-Kwai-Chult. It's a native Indian word. We're looking at an area here. It has got two pipes, the DO18, DO27. But the blue indicates water. So this pipe got a lake on top of it. This one doesn't. And this was flown with a number of PM systems. So here was the frequency domain system, and what we're looking at here is apparent conductivity. So this region up here, DO18, is a very conductive pipe, and this region is also conductive but lower. So you can see that you've got things that are going on here. Identifies a couple of pipes, so people kind of got excited about that. The time domain system at a particular time gives rise to this here, so it picks out the bottom pipe, but this one up. So those are the two. There's two systems. I won't even bother going into details, but what is the frequency domain? So this frequency was 6,000 hertz. And this is the time domain. It's the current waveform is a step off, and then you're measuring signal at 90 microseconds after the turn off. So those are your data. So here's our flow chart for the inverse problem. Okay. We're going to discretize the Earth and then follow through. So we need to be able to solve the forward problem. That means we need to solve Maxwell's equations. So I don't think I've actually shown this at this point, but here's Maxwell's equations in time and in frequency. I guess that everybody has seen these with constitutive relationships from the laboratory. So we need to solve those with particular sources and boundary conditions, and we need to discretize it. So what I want to show you in the next 4 or 5 slides. It's kind of technical, and you don't need to really know the details. That's really not that important. But I think what is important is kind of get an idea of what the level of complexity is for actually solving a serious one-day problem. And I also want to reinforce on you that you kind of have the tools to do that. So I'm going to show you how this problem is done. And I think by now you'll actually be able to relate to a lot of things that are going on when I show you a flow chart or something like that. Okay, I kind of get that. Okay, so let's do this. So let's suppose in the time domain system, so we got this loop out here. It's like 20 odd meters in diameter. And there's going to be a current that's going through. The current is actually going to look like this. It steps on, right? And then and then you turn it off. Can't turn it off instantly, but turn it off in the map, and you measure the magnetic field, EVT, at various time channels. So the procedure then is to, at any particular location, so the helicopter is flying over, I'm going to turn off the magnetic field. That means the time-varying magnetic field generates currents in the Earth. Those have magnetic fields. I can measure them appear in my receiver, and that's my data. And I go here, and the helicopter is going, 70 kilometers an hour. And so it's, it's here, 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 and then you gradually just build up all of that sequence of data. Okay, so those are Maxwell's equations, partial differential equations. Right, we got to do something. Right? So here's the two that are interesting. So curl E is minus dot E. So time varying flux generates an electric field. And then any kind of a current that you have also generates a magnetic field. So it's these combinations that give rise to the EM induction problem. Those are Maxwell's equations, and we have some boundary conditions, and we might have some initial conditions. Our goal is that we've got to discretize those equations both in space and in time. So let's take one at a time. Discretizing in space, we're going to use a staggered grid, and that means that we're going to define our physical properties at various places. So we're going to define sigma, for instance, at the center of cells, the electric fields on the edges, the B on the faces, the speed is a flux, and our continuous second-order differential equations that we have by combining everything can be written just in terms of the electric field and derivative of our source function. So that's our differential equation, so you get that analytically, right? And then now you've got to discretize that onto this mesh. That's where the finite volume comes in. And then ends up, we can write the discrete system of equations right here with matrices and vectors that actually look kind of like this. So this graph is actually, a C, well, this curl is like a C transpose, mu minus 1 corresponds to that. This curl corresponds to that. So curl, mu, curl transpose, okay, E plus M, so that's our sigma, dot E dot T, fifth, dot S. So this is actually really nice once you get to something like this, to have this discretization and a representation that, like you can look at the discrete mathematics and you actually can kind of see the operators that are happening in continuous field. So that was space. Now I have to do time. So remember, we have a ddt here, right? So that means we've got to do a time difference. So in order to time step, we use what's called a backward Euler, which allows us to compute the fields at step n plus 1 by looking at the source n plus 1 minus the previous one and the fields. So I have to remember the fields just before. And then we've got a system of equations. And then we get to solve this at each time step. So we get a system, so we've got an A matrix, a B matrix, and some source. And the other thing I mentioned earlier, but just kind of slipped it by, is that one of the big steps in being able to solve larger scale problems is the fact that we can now factor a lot of these matrices. So this is a surprise to many of us. Like 30 years ago, the prospect of taking a matrix and decomposing it into like an LL transpose. It was fine if you had up to 500 or 1,000 variables, right? But if you go to 1 million variables, there's no way. So then that meant you have to go with iterative solvers. Now, however, you can actually factor very large matrices with into something like this. So both Monks and Paradiso are two prime packages that can be. And then what we're going to do is to set up an iterative system whereby the fields at n plus 1, obtained from fields before it, And in the end, it turns out to be this sort of bi-diagonal system that you need to solve for the U's, which are all of the fields, the electric and magnetic fields at different node places, and here you have the right-hand side. So that's kind of how the gist gets set up. But let's just think about time. So the time, okay, it's going to be time to factor this matrix, which is and then the number of transmitters, and then time to solve each system. So those all get multiplied together, and then plus sort of the factorization time. So you've got these factors all to put together, and kind of depending upon how many partitions you have, that's sort of the total number of times that you effectively have to solve the forward problem. So now we got our inverse problem, we've got this, and nothing has changed from the right-hand side of all this. So we can solve the forward problem, and now we also know how to solve the inverse problem, right? So this is kind of what we're writing out. We take the gradient. Now we take Gaussian expansion. We need J. You have to think about J. That's going to be factored. And then we're going to solve this system using this a conjugate gradient, actually it's preconditioned, but the conjugate gradient technique, which involves taking this matrix and multiplying it on there. So the number of forward modeling your system is basically two times the number of solvers iterations. So maybe 20 or 30. So here's a flow that I think will make some sense to you. So here's our Gaussian approach. So we've got this system up here. So what are we going to do? Got to choose a beta knot. Got to choose an MRAM. So that's at the start. Now we've got to be easy, so we've got to calculate pi, MRAM, and we've got to calculate the gradient, and we've got to calculate these matrices, WD, all these W's up here. So now pi is range from 0 to some maximum number of iterations. Then we're going to solve this system of equations, so that's the Gauss-Newton equations for delta M. Do a line search with alpha, update the model, and exit. That's kind of what we've been doing all day, and just like nothing has changed. The only thing that changed is tallying the computations. Because suppose you just have 1,000 transmitters, which is not really enough. So you got 1,000 transmitters, and you got, let's suppose, a number of time steps in the time domain system. Let's suppose that's 50. Solving Gaussian step, that's 20. And the number of Gaussian iterations is 20. So the total number of times you have to solve Maxwell's equations in this is in the order of 20 million. Okay, starting that up. And remember, the Maxwell equation was actually pretty big, right? So you have to do that, let's say 20 million times. Even if you can factor that matrix in the order of a second, and you had 100 processors, it's still $55. And again, 1,000 processors, it's 5.5. So the only reason that we can now even think of solving this kind of problem is that we've got multiple processors. We've got cloud computing. And you can also see that within these kinds of problems, every detail that you can put together helps. If you can save a little bit on storage, you can make something a little bit faster. You can, every little, 10% or 50% accumulates and can. So one of the big things that has come up and just kind of surfaced here with this is if you're solving the forward problem on the great big mesh, it's way too big a problem. You've got maybe 10 million cells. If we have to solve this 20 million times, there's no hope. So I think one of the big advances recently is the use of semi-structured meshes. Some people go entirely semi-structured, like off-tree meshes, which allow you to, for a transmitter that's here, you've got a fine number of cells to the forward line, fine number of cells around here, so that your maximum equation is actually not too big. And then if you change the location of your transmitter, you've got another mesh. And if you change it, you have yet another mesh. So separating out the inversion mesh with local forward calling mesh is a huge deal. And that can save a lot of time. If we go back to PKC, we had the frequency domain data and the time domain data. We're able to put all of that together to get this 3D conductivity model. So this is a plan view, and you can see that there's two big conductors here, one for this pipe, like that, and this is the cross section that we've got, and you see what the outline of the conductivity is. So that's yeah, that was a very nice result. That's hard to get out, but yeah, we now have features and methodology and techniques. So in summary, for large scale inversions, and I think this is perhaps one of the important things, nothing has changed. We can use the same methodology for large scale as we did for the small or toy problems. And really, it's been the advances in scientific computing, direct solvers for any partial differential equation, semi-structured meshes, off-tree, separating the forward and the inverse mesh, handle large sensitivity metrics by doing that factorization, and access to multiverse. Those are the big ticket items that really allow us to take that next step. So I think with that, we should probably have coffee, right? Is coffee ready? And then let's just do that. I'm just trying to maybe address, is coffee ready or should I go on for that? Yeah, okay, so let's do that. And then, so what we'll do is look at this addressing of uncertainty, and then we'll wrap up.
Just put together a form. Oh, yeah. Go ahead.